Alright, in this video, we study some basic properties of differentiation. Let's start. So, the first property is linearity. Just like any other limits, derivatives are limits. So, it inherits some properties of limits, such as linearity, as I will describe now. So if we have two functions, let's say f of x and g of x, which are differentiable on some interval, and then if we differentiate a linear combination of these functions, so k is a real number, some constant, L is another constant, so k times f of x times L times g of x. So this is differentiation of a linear combination of these two functions, and the result is k times the derivative of f plus L times the derivative of g. So this means, this is of course df dx, and this is of course dg dx. So the derivative of a linear combination is a linear combination of the derivative. So that's the result. And I don't think we need to prove this. It's almost obvious, and you should try to show that based on the definition of the derivatives. So this was the first property. And the second property is about the derivative of a product of two functions. So, okay, so this is not equal to the product of derivatives. It's not equal to this, okay? Don't make this mistake. This is not equal to this, okay? It's wrong. But instead, we have this f prime times g. So this is not differentiated, plus f of x times g prime of x. So this is called the product rule. But, the name is not so important, but what's important is this fact. Okay, but anyway, let's write it down. It's called the product rule. All right, let's prove this. Okay, so to begin with, what's the definition of the derivative? Okay, so this is, by definition, is a limit. Let's say h goes to 0, and f of x plus h, g of x plus h, minus f of x times g of x, divided by h, right? So, this product is one function, okay? So let's say this is f of x. Okay, f of x is equal to capital F of x is equal to f of x times g of x. So this derivative should be equal to limit f of x plus h minus f of x divided by h, right? So if you substitute this x plus h into x, we have this here, and for this one, we have this here. Okay. So now what can we do? This is equal to, let's see. So we have x plus h here and here, but we want to convert this in terms of some, derivative of f and derivative of g. So why don't we f of x, add and subtract some same stuff. So for example, minus f of x times g of x plus h. Okay, so we subtract this term and add this term, same term, and minus this one, f of x, g of x. Sorry for it being ugly a little bit. Yes. And so let's consider this part. So we have this common factor here. So we can factorize. And for this one, we have this common factor, and we can factorize. So, this part and this part, they are just addition. Okay, so we can split the limit according to the first result. It's a linear combination, right? So this is f of x plus h minus f of x times g of x plus h divided by h, and minus this part. It's not minus, it's plus. Limit h going to 0, and f of x times g of x plus h minus g of x divided by h. Okay. Now, this part converges to f prime, and this part converges to g of x. Okay, this part doesn't contain h, so it is f of x. And this part converges to g prime, right? So the result is f prime of x times g of x plus f of x times g prime of x. And we are done. Okay, the third property is called the quotient rule. So it's about the ratio of functions. Okay, so don't make this mistake. This is not equal to f prime divided by g prime. Okay, this is wrong. Instead, this is equal to this, f prime times g of x minus f times g prime divided by g of x squared. Okay, of course this is defined only for only when g of x is non-zero. Okay, otherwise it cannot be defined. Okay, so let's prove this. So just apply the definition first. So f of x divided by g of x. So this is limit h going to 0. And so this whole thing is one function. Okay, so that is f of x plus h divided by g of x plus h minus f of x over g of x, everything divided by h. Okay, now limit h going to 0. So let's simplify this a little bit. So this becomes, let's see, let's make the common denominator. So that would be f x plus h g of x minus f of x gx plus h divided by g of x plus h g of x and divided by h. Okay, now let's see. So this is very similar to the previous example actually for this case, right? So we can use a similar technique. And that is, let's see, f of x plus h times g of x minus f of x times g of x plus, add the same thing, f of x, g of x minus f of x and gx plus h divided by, so let's put this h, this denominator here. So h and g of x plus h times g of x here. Okay. Now let's consider this part and this part. Okay. So factorize by g of x. times g of x. Let's divide it by h here. And let's put this out. G of x. Okay, so this is the first term. And let's put this term first. So we put this negative sign out. So that becomes, so factorized by f of x, we have f of x here, and g of x plus h minus g of x divided by h, and times this. Okay, so this part converges to f prime, and this part converges to g prime, and this part converges to g of x, and this part also converges to g of x. So in the end, we have f prime of x, g of x, and minus f of x, g prime of x, divided by this. So that is, we have g of x squared. G of x squared. So that's the result. Okay, so let's see a simple example. So let's differentiate tangent x. Okay, and tangent x by definition is sine of x over cosine of x. So we can use the quotient rule. So let's do that. And so first we differentiate the numerator, sine x prime times the denominator minus numerator times the derivative of the denominator divided by square of the denominator. Okay, so sine prime, differentiate sine function, we have cosine x, and we have cosine x here, so it's squared, cosine squared x. And here cosine x prime is negative sine x, so here we have negative sign, so negative times negative is positive, and we have sine squared x and cosine squared x. But cosine squared plus sine squared is equal to 1. So the numerator becomes 1 and the denominator is cosine x squared. So this is the derivative of tangent x. Okay, next let's consider the derivative of a composite function. So consider g after f of x. Okay, so this is a composite function, and in case you forgot, we define this as this. Okay, g after f of x is defined as g of f of x. Okay, so that means we first apply f to x, then to that result we apply the function g. Okay, so what do we get if we differentiate this composite function? So composite g of f of x. So what we have, and although we have this, it's not something like this, g prime of f prime of x. It's wrong. Okay, and it's not equal to g of f prime of x, and this is wrong. And the correct answer is g prime of f of x times f prime of x. Okay, and this is called the chain rule. Chain rule. Okay, so g prime means we just differentiate the function g, not inside. Okay, so as if this is a function of, let's say, some other variable called, let's say, y. So it's like if we differentiate the function g with respect to y, so g as a function of y. Okay, so that's g prime. Okay, So let's try to prove this. Okay, so just like always, we just apply the definition first. Okay, so g after f of x is, so this is g of f of x, right? And this is, by definition, is the limit. H going to 0, and g of f of x plus h minus g of f of x divided by h. Okay, now let's see what we can do. So, in the end we have g prime. And g prime means g something minus something. So that's something minus something should be in the denominator. So let's put that here. G of f of h minus g of f x plus h and g of f of x divide by the difference between these that are inside. Okay, so f of x plus h minus f of x inside. Okay, and times, so we divide by this and multiply by the same thing. So the effect is none, right? So we just multiply and divide by the same number. Okay, so this thing is equal to this thing times this thing. Okay, so everything inside the limit. Okay, now if h goes to 0, then f of x plus h goes to f of x. Okay, so this converges to this. So inside this converges to inside this. So that means this whole thing would converge to g prime of f of x. And this thing, of course, converges to f prime of x. So the result is, let's see. So the result is this limit times this limit. That is g prime of f of x times f prime of x. And we are done. For this chain rule, it may be easier to remember if we write like this. Y is equal to f of x, and z is equal to g of y. Of course, if we substitute this y equal to f of x, we get the same thing. So this is g of y is g of f of x. Okay, then the chain rule can be expressed as follows. So dz over dx is equal to dz over dy times dy dx. Okay, so what we did is just this. So differentiate this thing, g of f of x, then we get d g of y dy times, so dy is, dy means df of x, right? So we have this. So this part corresponds to z, and this part corresponds to z. Y is y, and this part corresponds to this, and dx is dx. So this is just like ordinary, multiplication of fractions. It just appears like that. It's not quite same as multiplication of fractions, but it looks the same. So it's easier to remember, I think. So let's see an application of the chain rule. Let's say f of x is any differentiable function. Okay, then we consider differentiating f of ax. Okay, where a is a constant. Okay, so of course, if we differentiate f of x, then we get f prime of x. Okay, then what if, this is like we are scaling the input by the factor of a. If we differentiate this, what do we get? So according to the to the chain rule, we have f prime of ax, so this inside doesn't change here, times, so now we differentiate this inside, so d of ax dx, which is just a, okay, f prime ax. So this is just a linear function, so the result is a, and we get a times f prime of ax. So if we scaled the input to a function, the derivative of the function is scaled by a. Okay, next let's consider the derivative of an inverse function over some given function. Okay, suppose we have y is equal to f of x, and assuming that this f is a bijection, then we have the inverse function of f. So we can write x is equal to f inverse of y. Now, what is the derivative of f inverse of y with respect to y? And this is actually given by this, 1 over f prime of f inverse of y. Okay, let's prove this. And first of all, we have y equals to f of x and x equals to f inverse of y. Now let's consider y as a function of x, just like this. So we have, maybe it's better if we write y of x here inside. So let's differentiate both sides with respect to x. Then the first, the left-hand side is just dx over dx, that is 1. Okay, and the right-hand side is the function. So this is a composite function, so we can apply the chain rule. And this we have d f inverse dy dx. And so f inverse dy times dy dx is f prime of x, right? Because y is equal to f of x. So this is what we want, and that is equal to the left-hand side, which is equal to 1. Therefore, the derivative of f inverse with respect to y is equal to 1 over f prime of x. But x is equal to this. So we have 1 over f prime of f inverse of y. And that's it. Okay, let's see an example. So let's differentiate arcsine function. So this should be equal to square root of 1 over square root of 1 over square root of 1 minus x squared, where x is between -1 and 1. Okay, let's prove this. First of all, let's put y equals to arc sine x, and x is between -1 and 1, and arc sine by definition is the inverse of sine function, so we have x equals to sine y, and here y, this the domain of sine function is between -π½ and +π². So that is -π½ and y +π². Okay, now we apply the derivative, find the derivative of both sides of this. Okay, so if we differentiate both sides by x with respect to x, then we have 1 equal to sine y. If we apply the chain rule, so sine y dy and dy dx. And this term is cosine y. And dy dx, that is what we want here, right? So d dx arc sine x. So therefore, the derivative of arc sine function is equal to 1 over cosine y. And cosine y is, okay, if you remember this identity, sine squared plus cosine, let's use y here. And cosine squared y is equal to 1. So cosine y is equal to square root of 1 minus sine squared y, right? And since we are considering only this interval, cosine y is always positive. To see that, maybe you should plot. So the unit circle, any point on the unit circle, the x coordinate gives cosine theta, and the y coordinate gives sine theta. Okay, since we're considering this interval, the angle varies between this and this, and in this interval, so this is so this angle is negative pi half, and this angle is positive pi half. So in this interval, the cosine function is always positive, so we can take the positive square root like this. Okay, now, and sine y is x, okay, because y is equal to arc sine x, therefore x is equal to sine y. So sine y squared is equal to 1 x squared. So we have 1 over square root of 1 minus x squared. So this is it. Okay, another example. Let's consider y equals to x to the power of a, where a is any real number. Okay. And we already know that when a happens to be a natural number, then the derivative of this function is just a times x to the power of a minus 1. But actually this equality holds for any real number a, not just for natural numbers. So let's prove that. To see this, first we want to express x to the power of a in terms of exponential function. So y equals to x to the power of a is equal to e to the power of a times log of x. So this log is the natural logarithm. So can you see how this holds? It's actually easy. So just pick this original definition here. So let's take the natural logarithm of both sides. So that is log y is equal to log of x to the power of a. But from the property of the logarithm, we have a log x here. Now, let's take the exponential function of both sides. Then, since log and exponential function, they are just inverse of each other. So log of y, exponential of log of y is just y, right? Then that's the left-hand side, and the right-hand side is e to the power of a log of x. So that's how we get this. Now, let's differentiate this function. So dy dx is equal to d e a log of x. Now, we can use the chain rule. So first, differentiate e to the power of something. But that is just e to the power of that something. So e a log of x. okay, times the derivative of this exponent, a log of x. So this is just chain rule, and a log of x times, so this one is a times, so the derivative of log of x is 1 over x. Okay, and this one is this, right? So we have x to the power of a times, so this a divided by x. So that is a times x to the power of a minus 1. So that's what it is. Now, let's consider higher order differentiation. That is, if we have a function f of x that is differentiable, then we get, if we differentiate this function, we get f prime of x. That is the derivative of f. But now, this derivative itself is also a function. Okay? Therefore, we can consider whether it is differentiable or not. So if we can differentiate this function, then maybe we can get the second derivative. And we can continue this process on and on. So this may be differentiable. If it is, then we can find the third derivative and fourth derivative. So, if there are too many primes here, it's hard to see. So usually from the fourth derivative, we write like this. Fourth derivative, fifth derivative, and so on. A simple example is, let's say, x to the power of 10. Okay. So if we differentiate this, we get f prime of x, that is 10 times x to the power of 9. And this is, again, a differentiable function. So if we can differentiate it, f double prime, the second derivative, is 10. So that's 9 times 10 times x to the power of 9 minus 1, that's 8. So 90 times x to the power of 8. So that's the second derivative. And you can also differentiate this function again, and then again, and again. And another simple example is f of x is equal to e to the power of x. Okay, if you differentiate this, it doesn't change, right? And so this is again the same function as this one. So we can differentiate forever, infinitely many times. Next, let's consider a function that is not infinitely many times differentiable. Here's that example. F of x is defined as x squared if x is positive or 0, or negative x squared when x is negative. So when x is strictly positive, then we can differentiate with no problem, and the result is 2x. And when x is strictly negative, then we can again differentiate this function, and the derivative is negative 2x. And what about x equal to 0? Then what is the derivative? Can we even define it? The answer is yes. So let's see that. So to see for the differential coefficient at x equal to 0 to be defined, then the right limit and the left limit must match. So let's see that. X going to 0 from the right. So x, in that case, x is positive, so we have x squared. Since we are considering the derivative at x equal to 0, then x, we consider 0 squared, so x minus 0. And that is, let's see, so this is just limit x, so x squared divided by x is just x. And that is 0. Okay, and let's consider the left limit, x going to 0 from the left. In that case, x is negative. So we have negative x squared minus 0 squared, 0 squared, yeah, 0 squared divided by x minus 0. Okay, so in this case we have negative x. But this limit is again 0. So the right limit and the left limit, they are the same. So the differential coefficient at x equal to 0 is 0. So we can define this function, this derivative. So either this when x is positive, or this when x is negative, and 0. And this is continuous function, right? So we can actually summarize these three cases in just one expression. That is, f prime of x is equal to 2 times absolute value of x, right? You know, x is negative, we have negative 2x. So that is, the derivative itself is positive. So we can summarize like this. However, this function is not differentiable anymore. So it's not differentiable at x equal to 0. Therefore, this is only one-time differentiable. So let's define the notion of higher derivatives or higher order derivatives. Okay, so we have already defined the derivative of a function f like this. And if we differentiate this, so we can differentiate this again. And this one we write like this, d2 f over dx squared. Okay, or we can write f double prime as we have already seen. And again, we can differentiate this. So d2 dx2, and we write this, the third derivative, d3 f dx3, or we write f triple prime. And we can continue this again, yeah, as long as the function, the derivative is differentiable. So this we write d4 f dx4, or f parenthesis 4 of x. So fourth derivative or fourth order derivative, and so on. So we can continue this, and if for the derivative that is obtained by differentiating n times, we write like this, dn f dxn, or f parenthesis n of x, so nth derivative. Now we define some term here. We say a function f of x is of class Cn. Okay, if and only if the derivatives f prime, f double prime, and so on up to the nth derivative exist, and all of them are continuous and are continuous. Okay, so all of these, not just first, second, or third, but up to nth derivative, they all exist and all of them are continuous. Then we say this function f of x is of class Cn. And if we can differentiate this function infinitely many times, okay, then we say f of x is of class C infinity. Okay, so this means all the derivatives, higher order derivatives exist, and since they can be differentiated indefinitely, all of them are continuous, of course. So if that's the case, then the function is called to be of class C infinity. Example of C infinity function is exponential of x. As we have seen, when differentiated, this function doesn't change, so we can just infinitely many times differentiate it. An example, this function, this is of class what? This is not differentiable at all, but it is continuous, so it's of class C0. Okay, and the function we have seen a little bit ago, defined as like x squared when x is positive or 0, or negative x squared when x is negative. This function we can differentiate once, but not twice. So this is class C1. Okay, so that's all for this video. See you later.